All right. Next is chemistry. So let's back out of that, back out of there. Let's go to science, chemistry 2E. Download, go to file. Man, I had some really good thoughts today. I can't wait to talk about them, but it'll be a little while before I do that. Boom, boom. Chapter 1, Essential Ideas. Chapter outline, Chemistry and Context. Phases and classification of matter. Physical and chemical properties. Measurements. Measurement uncertainty, accuracy, and precision. Mathematical treatment of measurement results. Your alarm goes off, and after hitting snooze once or twice, you pry yourself out of bed. You make a cup of coffee to help you get going, and then you shower, get dressed, eat breakfast, and check your phone for messages. On your way to school, you stop to fill your car's gas tank, almost making you late for the first day of chemistry class. As you find a seat in the classroom, you read the question projected on the screen. Welcome to class. Why should we study chemistry? Do you have an answer? You may be studying chemistry because it fulfills an academic requirement, but if you consider your daily activities, you might find chemistry interesting for other reasons. Most everything you do and encounter during your day involves chemistry. Making coffee, cooking eggs, toasting bread involve chemistry. The products you use, like soap and shampoo, the fabrics you wear, the electronics that keep you connected to your world, the gasoline that propels your car, all of these and more involve chemical substances and processes. Whether you are aware or not, chemistry is part of your everyday world. In this course, you will learn many of the essential principles underlying the chemistry of modern day life. 1.1, Chemistry and Context. Learning objectives. By the end of this section, you will be able to outline the historical development of chemistry, provide examples of the importance of chemistry in everyday life, describe the scientific method, differentiate among hypotheses, theories, and laws, provide examples illustrating macroeconomic or microscopic, and symbolic domains. Throughout human history, people have tried to convert matter into more useful forms. Our Stone Age ancestors chipped pieces of flint into useful tools and carved wood into statues and toys. These endeavors involved changing the shape of a substance without changing the substance itself. But as our knowledge increased, humans began to change the composition of the substances as well. Clay was converted into pottery, hides were cured to make garments, copper ores were transformed into copper tools and weapons, and grain was made into bread. Humans began to practice chemistry when they learned to control fire and use it to cook, make pottery, and smelt metals. Subsequently, they began to separate and use specific components of matter. A variety of drugs, such as aloe, myrrh, and opium, were isolated from plants. Dyes, such as indigo and Tyrian purple, were extracted from plant and animal matter. Metals were combined to form alloys. For example, copper and tin were mixed together to make bronze, and more elaborate smelting techniques produced iron. Alkalis were extracted from ashes, and soaps were prepared by combining these alkalis with fats. Alcohol was produced by fermentation and purified by distillation. Attempts to understand the behavior of matter extend back for more than 2,500 years. As early as the 6th century BC, Greek philosophers discussed a system in which water was the basis of all things. You may have heard of the Greek postulate that matter consists of 4 elements: earth, air, fire, and water. Subsequently, an amalgamation of chemical technologies and philosophical speculations was spread from Egypt, China, and Eastern Mediterranean by alchemists, who endeavored to transform base metals such as lead into noble metals like gold, and to create elixirs to cure disease and extend life. From alchemy came the historical progressions that led to modern chemistry, the isolation of drugs from natural sources, such as plants and animals. But while many of the substances extracted or processed from those natural sources were critical in the treatment of diseases, many were scarce. For example, Progesterone, which is critical to women's health, became available as a medicine in 1935, but its animal sources produced extremely small quantities, limiting its availability and increasing its expense. Likewise, in the 1940s, cortisone came into use to treat arthritis and other disorders and injuries, but it took a 36-step process to synthesize. Chemist Percy Lavon Julian turns to a more plentiful source, soybeans. Previously, Julian had developed a lab to isolate soy protein, which was used in firefighting among other applications. He focused on using soy sterols, substances mostly used in plant membranes, and was able to quickly produce progesterone and later testosterone and other hormones. He later developed a process to do the same for cortisone and laid the groundwork for modern drug design. Since soybeans and similar plant sources were extremely plentiful, the drug soon became widely available, saving many lives. Chemistry, the central science. Chemistry is sometimes referred to as the central science due to its interconnectedness with a vast array of other STEM disciplines. Chemistry and the language of chemists play vital roles in biology, medicine, material science, forensics, environmental science, and many other fields. The basic principles of physics are essential for understanding many aspects of chemistry, and there is extensive overlap between many subdisciplines within the two fields, such as chemical physics and nuclear chemistry. Mathematics, computer science, and information theory provide important tools that help us calculate, interpret, describe, and generally make sense of the chemical world. Biology and chemistry converge in biochemistry, which is crucial to understanding the many complex factors and processes that keep living organisms alive. Chemical engineering, material science, and nanotechnology combine chemical principles and empirical findings to produce useful substances ranging from gasoline to fabrics to electronics. Agriculture, food science, veterinary science, and brewing and wine making help provide sustenance in the form of food and drink to the world's population. Medicine, pharmacology, biotechnology, and botany identify and produce substances that help keep us healthy. Environmental science, geology, oceanography, and atmospheric science incorporate many chemical ideas to help us better understand and protect our physical world. Chemical ideas are used to help understand the universe in astronomy and cosmology. Oh, that's cool. I might have to write this, get this down. No, because I'm gonna come up with my own version. That's gonna work out pretty well. What are some changes in matter that are essential to daily life? Digesting and assimilating food, synthesizing polymers that are used to make clothing, containers, cookware, and credit cards, and refining crude oil into gasoline and other products are just a few examples. As you proceed through this course, you will discover many different examples of changes in the composition and structure of matter, how to classify these changes and how they occurred, their causes, the changes in energy that accompany them, and the principles and laws involved. As you learn about these things, you will be learning chemistry, the study of the composition, properties, and interactions of matter. The practice of chemistry is not limited to chemistry books or laboratories. It happens whenever someone is involved in changes in matter or in conditions that may lead to such changes. The scientific method. Chemistry is a science based on observation and experimentation. Doing chemistry involves attempting to answer questions and explain observations in terms of the laws and theories of chemistry, using procedures that are accepted by the scientific community. There is no single route to answering a question or explaining an observation, but there is an aspect common to every approach. Each uses knowledge based on experiments that can be reproduced to verify the results. Some routes involve a hypothesis, a tentative explanation of observations that acts as a guide for gathering and checking information. A hypothesis is tested by experimentation, calculation, and/or comparison with the experiments of others and then refined as needed. Some hypotheses are attempts to explain the behavior that is summarized in laws. The laws of science summarize a vast number of experimental observations and describe or predict some facet of the natural world. If such a hypothesis turns out to be capable of explaining a large body of experimental data, it can reach the status of a theory. Scientific theories are well-substantiated, comprehensive, testable explanations of particular aspects of nature. Theories are accepted because they provide satisfactory explanations, but they can be modified if new data becomes available. The path of discovery that leads from question and observation to law and/or hypothesis to theory combined with experimental verification of the hypothesis and any modification of the theory, is called the scientific method. The domains of chemistry. Chemists study and describe the behavior of matter and energy in three different domains: macroscopic, microscopic, and symbolic. These domains provide different ways of considering and describing chemical behavior. Macro is a Greek word that means large. The macroscopic domain is familiar to us. It is the realm of everyday things that are large enough to be sensed directly by human sight or touch. In daily life, this includes the food you eat and the breeze you feel on your face. The macroscopic domain includes everyday and laboratory chemistry, where we observe and measure physical and chemical properties such as density, solubility, and flammability. Micro comes from the Greek and means small. The microscopic domain of chemistry is often visited in the imagination. Some aspects of the microscopic domain are visible through standard optical microscopes, for example, many biological cells. More sophisticated instruments are capable of imaging even smaller entities such as molecules and atoms. However, most of the subjects in the microscopic domain of chemistry are too small to be seen even with the most advanced microscopes, and may only be pictured in the mind. Other components of the microscopic domain include ions, electrons, protons and neutrons, and chemical bonds, each of which is far too small to see. The symbolic domain contains the specialized language used to represent components of the macroscopic and microscopic domains. Chemical symbols, chemical formulas, and chemical equations are part of the symbolic domain, as are graphs, drawings, and calculations. These symbols play an important role in chemistry because they help interpret the behavior of the macroscopic domain in terms of the components of the microscopic domain. One of the challenges for students learning chemistry is recognizing that the same symbols that can represent different things in the macroscopic and microscopic domains, and one of the features that makes chemistry fascinating is the use of a domain that must be imagined to explain behavior in a domain that can be observed. A helpful way to understand the three domains is via the essential and ubiquitous substance of water. That water is a liquid at moderate temperatures, will freeze to form a solid at lower temperatures, and boil to form a gas at higher temperatures, are macroscopic observations. But some properties of water fall into the microscopic domain. What cannot be observed with the naked eye? The description of water is comprising of 2 hydrogen atoms and 1 oxygen atom, and the explanation of freezing and boiling in terms of attractions between these molecules is within the microscopic arena. The formula H2O, which can describe water at either the macroscopic or microscopic levels, is an example of the symbolic domain. The abbreviations for gas, for solid, and liquid are also symbolic. 1.2 Phases and classification of matter. Learning objectives. By the end of this section, you will be able to describe the basic properties of each physical state of matter, solid, liquid, and gas, distinguish between mass and weight, apply the law of conservation of matter, classify matter as an element, compound, homogeneous mixture, or heterogeneous mixture with regard to its physical state and composition, define and give examples of atoms and molecules. Matter is defined as anything that occupies space and has mass, and it is all around us. Solids and liquids are more obviously matter. We can see that they take up space, and their weight tells us that they have mass. Gases are also matter. If gases did not take up space, a balloon would not inflate when filled with gas. Solids, liquids, and gases are the 3 states of matter commonly found on Earth. A solid is rigid and possesses a definite shape. A liquid flows and takes the shape of its container, except that it forms a flat or slightly curved upper surface when acted upon by gravity. Both liquid and solid samples have volumes that are very nearly independent of pressure. A gas takes both the shape and volume of its container. A 4th state of matter, plasma, occurs naturally in the interiors of stars. A plasma is a gaseous state of matter that contains appreciable numbers of electrically charged particles. The presence of these charged particles imparts unique properties to plasmas that justify their classification as a state of matter distinct from gases. In addition to stars, plasmas are found in some other high-temperature environments, both natural and man-made, such as lightning strikes, certain television screens, and specialized analytical instruments used to detect trace amounts of metals. Some samples of matter appear to have properties of solids, liquids, and/or gases at the same time. This can occur when the sample is composed of many small pieces. For example, we can pour sand as if it were a liquid because it is composed of many small grains of solid sand. Matter can also have properties of more than one state when it is a mixture, such as with clouds. Clouds appear to behave somewhat like gases, but they are actually mixtures of air and tiny particles of water. The mass of an object is a measure of the amount of matter in it. One way to measure an object's mass is to measure the force it takes to accelerate the object. It takes much more force to accelerate a car than a bicycle because the car has much more mass. A more common way to determine the mass of an object is to use a balance to compare its mass with a standard mass. Although weight is related to mass, it is not the same thing. Weight refers to the force that gravity exerts on an object. This force is directly proportional to the mass of an object. The weight of an object changes as the force of gravity changes, but its mass does not. An astronaut's mass does not change just because she goes to the moon, but her weight on the moon is only 1/6 her Earth-bound weight because the moon's gravity is only 1/6 that of the Earth's. She may feel weightless during her trip when she experiences negligible external forces, although she is, of course, never massless. The law of conservation of matter summarizes many scientific observations about matter. It states that there is no detectable change in the total quantity of matter present when matter converts from one type to another, or changes among solid, liquid, or gaseous states. Brewing beer and the operation of batteries provide examples of the conservation of matter. During the brewing of beer, the ingredients are converted into beer, with no actual loss of substance. This is most clearly seen during the bottling process, when glucose turns into ethanol and carbon dioxide and the total mass of the substances does not change. This can be also seen in a lead-acid car battery. The original substances, which are capable of producing electricity, are changed into other substances that do not produce electricity, with no change in the actual amount of matter. Although this conservation law holds true for all conversions of matter, convincing examples are few and far between because, outside of the controlled conditions in a laboratory, we seldom collect all the material that is produced during a particular conversion. For example, when you eat, digest, and assimilate food, all the matter in the original food is preserved. But because some of the matter is incorporated into your body and much is excreted as various types of waste, it is challenging to verify by measurement. Classifying matter. Sorry. Matter can be classified into several categories. Two broad categories are mixtures and pure substances. A pure substance has a constant composition. All specimens of a pure substance have exactly the same makeup and properties. Any sample of sucrose consists of 42.1% carbon, 6.5% hydrogen, and 51.4% oxygen by mass. Any sample of sucrose also has the same physical properties, such as melting point, color, and sweetness, regardless of the source from which it is isolated. Pure substances may be divided into two classes, elements and compounds. Pure substances that cannot be broken down into simpler substances by chemical changes are called elements. Iron, silver, gold, aluminum, sulfur, oxygen, and copper are familiar examples of the more than 100 known elements, of which about 90 occur naturally on the Earth, and 24 or so have been created in laboratories. Pure substances that are comprised of two or more elements are called compounds. Compounds may be broken down by chemical changes to yield either elements or other compounds or both. Mercury 2 oxide, sorry, an orange crystalline solid can be broken down by heat into the elements mercury and oxygen. When heated in the absence of air, the compound sucrose is broken down into the element carbon and the compound water. Silver 1 chloride is a white solid that can be broken down into its elements, silver and chlorine, by absorption of light. This property is the basis for the use of this compound in photographic films and photochromic eyeglasses. Oops. Uh-oh. Uh-oh. Oh my gosh. Okay. The properties of combined elements are different from those in the free or uncombined state. For example, like crystalline sugar is a compound resulting from the chemical combination of the element carbon, which is a black solid in one of its uncombined forms, and the two elements, hydrogen and oxygen, which are colorless gases when uncombined. Free sodium, an element that is soft, shiny, metallic, solid, and free chlorine, an element that is yellow-green gas, combined to form sodium chloride, a compound that is a white crystalline solid. A mixture is composed of two or more types of matter that can be present in varying amounts and can be separated by physical changes such as evaporation. A mixture with a composition that varies from point to point is called a heterogeneous mixture. Italian dressing is an example of a heterogeneous mixture. Its composition can vary because it may be prepared from varying amounts of oil, vinegar, and herbs. It is not the same from point to point throughout the mixture. One drop may be mostly vinegar, whereas a different drop may be mostly oil or herbs because the oil and vinegar separate and the herbs settle. Other examples of, I think I should say heterogeneous mixtures are chocolate chip cookies and granite. A homogeneous mixture, also called a solution, exhibits a uniform composition and appears visually the same throughout. An example of a solution is a sports drink consisting of water, sugar, coloring, flavoring, and electrolytes mixed together uniformly. Each drop of a sports drink tastes the same because each drop contains the same amount of water, sugar, and other components. Note that the composition of a sports drink can vary. It can be made with somewhat more or less sugar, flavoring, and other components, and still be a sports drink. Other examples of homogeneous mixtures include air, maple syrup, gasoline, and a solution of salt and water. Although there are just over 100 elements, tens of millions of chemical compounds result from different combinations of these elements. Each compound has a specific composition and possesses definite chemical and physical properties that distinguish it from all other compounds. And of course, there are innumerable ways to combine elements and compounds to form different mixtures. A summary of how to distinguish ways the various major classifications of matter is shown in Figure 111. Okay. 11 elements make up about 99% of Earth's crust and atmosphere. Oxygen constitutes nearly 1/2, and silicon about 1/4 of the total quantity of these elements. A majority of elements on Earth are found in chemical combinations with other elements. About 1/4 of the elements are also found in the free state. Atoms and molecules. An atom is the smallest particle of an element that has the properties of that element that can enter into a chemical combination. Consider the element gold, for example. Imagine cutting a gold nugget in half, then cutting one of the halves in half, and repeating this process until a piece of gold remained that was so small that it could not be cut in half. This minimally sized piece of gold is an atom. This atom would no longer be gold if it were divided any further. The first suggestion that matter is composed of atoms is attributed to the Greek philosophers Leucippus and Democritus, who developed their ideas in the 5th century BCE. However, it was not until the early 19th century that John Dalton, a British schoolteacher with a keen interest in science, supported this hypothesis with quantitative measurements. Since that time, repeated experiments have confirmed many aspects of this hypothesis, and it has become one of the central theories of chemistry. Other aspects of Dalton's atomic theory are still used, but with minor revisions. An atom is so small that its size is difficult to imagine. One of the smallest things we can see with our unaided eye is a single thread of a spider web. These strands are about 1/10,000th of a centimeter in diameter. Although the cross-section of one strand is almost impossible to see without a microscope, it is huge on an atomic scale. A single carbon atom in the web has a diameter of about 0.00000015 centimeter, and it would take about 7,000 carbon atoms to span the diameter of the thread. That's so crazy. To put this in perspective, if a carbon atom were the size of a dime, the cross-section of one strand would be larger than a football field, which would require about 150 million carbon atom dimes to cover it. This increasingly close microscopic and atomic level views of ordinary cotton. An atom is so light that its mass is also difficult to imagine. A billion lead atoms weigh about 3 times 10 to the negative 13 grams. A mass that is far too light to be weighed on even the world's most sensitive balances. It would require over 300, that's million, billion, trillion lead atoms to be weighed, and they would weigh only 0.000001 gram. It is rare to find collections of individual atoms. Only a few elements, such as the gases helium, neon, and argon, consist of a collection of individual atoms that move about independently of one another. Other elements, such as the gases hydrogen, nitrogen, oxygen, and chlorine, are composed of units that consist of pairs of atoms. One form of the element phosphorus consists of units composed of 4 phosphorus atoms. The element sulfur exists in various forms, one of which consists of units composed of 8 sulfur atoms. These units are called molecules. A molecule consists of 2 or more atoms joined by strong forces called chemical bonds. The atoms in a molecule move around as a unit, much like the cans of a soda and in the six-pack, or a bunch of keys joined together on a single keyring. A molecule may consist of 2 or more identical atoms, as in the molecules found in the elements hydrogen, oxygen, and sulfur, or it may consist of 2 or more different atoms, as in the molecules found in water. Each water molecule is a unit that contains 2 hydrogen atoms and 1 oxygen atom. Each glucose molecule is a unit that contains 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. Like atoms, molecules are incredibly small and light. If an ordinary glass of water were enlarged to the size of the Earth, the water molecules inside it would be about the size of golf balls. Jeez. All right, 1.3. Physical and chemical properties. Learning objectives. By the end of this section, you will be able to identify properties of and changes in matter as physical or chemical, identify properties of matter as extensive or intensive. The characteristics that distinguish one substance from another are called properties. A physical property is a characteristic of matter that is not associated with a change in its chemical composition. Familiar examples of physical properties include density, color, hardness, melting, and boiling points, and electrical conductivity. Some physical properties, such as density and color, may be observed without changing the physical state of the matter. Other physical properties, such as the melting temperature of iron or the freezing temperature of water, can only be observed as matter undergoes a physical change. A physical change is a change in the state of or properties of matter without any accompanying change in the chemical identities of the substance contained in the matter. I just had a really, really interesting idea, and I hope I think of it again, because that would totally change the way. That would be a really interesting thing to study. Physical change is a change in the state or properties of matter without any accompanying change in the chemical identities of the substances contained in the matter. Physical changes are observed when wax melts, when sugar dissolves in coffee, and when steam condenses into liquid water. Other examples of physical changes include magnetizing and demagnetizing metals and grinding solids into powders. In each of these examples, there is a change in the physical state, form, or properties of the substance, but no change in its chemical composition. Interesting. Is water a plasma, or can it be considered plasma-like? The change of one type of matter into another type is a chemical property. Examples of chemical properties include flammability, toxicity, acidity, and many other types of reactivity. Iron, for example, combines with oxygen in the presence of water to form rust. Chromium does not oxidize. Nitroglycerin is very dangerous because it explodes easily. Neon poses almost no hazard because it is very unreactive. A chemical change always produces one or more types of matter that differ from the matter present before the change. The information of rust, the formation of rust, is a chemical change because rust is a different kind of matter than the iron, oxygen, and water present before the rust formed. The explosion of nitroglycerin is a chemical change because the gases produced are very different kinds of matter from the original substance. Other examples of chemical changes include reactions that are performed in a lab, all forms of combustion, and food being cooked, digested, or rotting. Yeah, these pictures are making it really difficult to. So properties of matter fall into one of two categories. If the property depends on the amount of matter present, it is an extensive property. The mass and volume of a substance are examples of extensive properties. For instance, a gallon of milk has a larger mass than a cup of milk. The value of an extensive property is directly proportional to the amount of matter in question. If the property of a sample of matter does not depend on the amount of matter present, it is an intensive property. Temperature is an example of an intensive property. If the gallon and cup of milk are each at 20 degrees Celsius when they are combined, the temperature remains at 20 degrees Celsius. As another example, consider the distinct but related properties of heat and temperature. A drop of hot cooking oil spattered on your arm causes brief, minor discomfort, whereas a pot of hot oil yields severe burns. Both the drop and the pot of oil are at the same temperature, but the pot clearly contains much more heat. While many elements differ dramatically in their chemical and physical properties, some elements have similar properties. For example, many elements conduct heat and electricity well, whereas others are poor conductors. These properties can be used to sort the elements into three classes: metals, nonmetals, and metalloids. A periodic table is a table of elements that places elements with similar properties close together. You will learn more about the periodic table as you continue your study of chemistry. 1.4 Measurements. Learning objectives. By the end of this section, you will be able to explain the process of measurements, identify the three basic parts of quantity, describe the properties and units of length, mass, volume, density, temperature, and time, perform basic calculations and conversions in the metric and other unit systems. Measurements provide much of the information that informs the hypotheses, theories, and laws describing the behavior of matter and energy in both the macroscopic and microscopic domains of chemistry. Every measurement provides three kinds of information: the size or magnitude of the measurement, a standard of comparison for the measurement, and an indication of the uncertainty of the measurement. While the number and the unit are explicitly represented when a quantity is written, the uncertainty is an aspect of the measurement result that is more implicitly represented and will be discussed later. The number in the scientific measurement can be represented in different ways, including decimal form and scientific notation. For example, the maximum takeoff weight of a Boeing 777-200ER airliner is 298,000 kilograms, which can also be written as 2.98 times 10 to the 5 kilograms. The mass of an average mosquito is about 0.000025 kilograms. which can be written as 2.5 times 10 to the negative 6 kilograms. Units, such as liters, pounds, and centimeters, are standards of comparison for measurements. A 2-liter bottle of a soft drink contains a volume of beverage that is twice that of the accepted volume of 1 liter. The meat used to prepare a 0.25-pound hamburger weighs 1/4 as much as the accepted weight of 1 pound. Without units, a number can be meaningless, confusing, or possibly life-threatening. Suppose a doctor prescribes phenobarbital to control a patient's seizures and states the dosage of 100 without specifying units. Not only will this be confusing to the medical professional giving the dose, but the consequences can be dire. 100 milligrams given 3 times per day can be effective as an anticonvulsant, but a single dose of 100 grams is more than 10 times the lethal amount. The measurement unit for 7 fundamental properties are listed in Table 1.2. The standards for these units are fixed by international agreement, and they are called the International System of Units, or SI units. SI units have been used by the United States National Institute of Standards and Technology since 1964. Units for other properties may be derived from these 7 base units. Everyday measurement units are often defined as fractions or multiples of other units. Milk is commonly packaged in containers of 1 gallon, 1 quart, and 1 pint. This same approach is used with SI units, but these fractions or multiples are always powers of 10. Fractional or multiple SI units are named using a prefix and the name of the base unit. For example, a length of 1,000 meters is also called a kilometer because the prefix kilo means 1,000, which in scientific notations is 10 to the third. The prefix is used and the powers to which 10 are raised are listed in Table 1.3. SI base units. The initial units of the metric system, which eventually evolved into the SI system, were established in France during the French Revolution. The original standards for the meter and the kilogram were adopted there in 1799 and eventually by other countries. This section introduces 4 of the SI base units commonly used in chemistry. Other SI units will be introduced in subsequent chapters. Length. The standard unit of length in both the SI and original metric systems is the meter. A meter was originally specified as 1/10,000,000th of the distance from the North Pole to the equator. It is now defined as the distance light in a vacuum travels in 299,792,458th of a second. A meter is about 3 inches longer than a yard. 1 meter is about 39.37 inches, or 1.094 yards. Longer distances are often reported in kilometers, whereas shorter distances can be reported in centimeters or millimeters. Mass. The standard unit of mass in the SI system is the kilogram. The kilogram was previously defined by the International Union of Pure and Applied Chemistry as the mass of a specific reference object. This object was originally 1 liter of pure water, and more recently, it was a metal cylinder made from a platinum-iridium alloy with a height and diameter of 39 millimeters. In May 2019, this definition was changed to one that is based instead on precisely measured values of several fundamental physical constants. 1 kilogram is about 2.2 pounds. The gram is exactly equal to 1/1000th of the mass of the kilogram. Temperature. Temperature is an intensive property. The SI unit of temperature is the Kelvin. The IUPAC convention is to use Kelvin for the word K for the unit symbol, and neither the word degree nor the degree symbol. A degree Celsius is also allowed in the SI system, with both the word degree and the degree symbol used for Celsius measurements. Celsius degrees are the same magnitude as those of Kelvin, but the two scales place their zeros in different places. Water freezes at 273.15 K and boils at 373.15 K by definition, and normal human body temperature is approximately 310 K. The conversion between these two units and the Fahrenheit scale will be discussed later in this chapter. Time. The SI base unit of time is the second. Small and large time intervals can be expressed with the appropriate prefixes. For example, 3 microseconds, 0.000003, or 3 times 10 to the negative 6, and 5 megaseconds, 5000000 equals 5 times 10 to the 6 seconds. Alternatively, hours, days, and years can be used. Derived SI units. We can derive many units from the 7 SI base units. For example, we can use the base unit of length to define a unit of volume, and the base units of mass and length to define a unit of density. Volume. Volume is the measure of the amount of space occupied by an object. The standard SI unit of volume is defined by the base unit of length. The standard unit is a cubic centimeter, a cube with an edge length of exactly 1 meter. To dispense a cubic meter of water, we could build a cubic box with edge lengths of exactly 1 meter. This box would hold a cubic meter of water or any other substance. A more commonly used unit of volume is derived from the decimeter. A cube with edge lengths of exactly 1 decimeter contains the volume of 1 cubic decimeter. A liter is the more common name for the cubic decimeter. 1 liter is about 1.06 quarts. A cubic centimeter is the volume of a cube with an edge length of exactly 1 centimeter. The abbreviation cc is often used by health professionals. A cubic centimeter is equivalent to a milliliter and is 1/1000th of a liter. Density. We use the mass and volume of a substance to determine its density. Thus, the units of density are defined by the base units of mass and length. The density of a substance is a ratio of mass from a sample of the substance to its volume. The SI unit for density is the kilogram per cubic meter. For many situations, however, this is an inconvenient unit, and we often use grams per cubic centimeter for the densities of solids and liquids, and grams per liter for gases. Although there are exceptions, most liquids and solids have densities that range from about 0.7 grams per centimeters cubed to 19 grams per centimeters cubed. The density of air is about 1.2 grams per liter. While there are many ways to determine the density of an object, perhaps the most straightforward method involves separately finding the mass and volume of the object, and then dividing the mass of the sample by its volume. In the following example, the mass is found directly by weighing, but the volume is found indirectly through length measurements. 1.5. Measurement uncertainty, accuracy, and precision. Learning objectives. By the end of this section, you will be able to define accuracy and precision, distinguish exact and uncertain numbers, correctly represent uncertainty in quantities using significant figures, apply proper rounding rules to computed quantities. Counting is the only type of measurement that is free from uncertainty, provided the number of objects being counted does not change while the counting process is underway. The result of such a counting measurement is an example of an exact number. By counting the eggs in a carton, one can determine exactly how many eggs the carton contains. The number of defined quantities are also exact. By definition, 1 foot is exactly 12 inches, 1 inch is exactly 2.54 centimeters, and 1 gram is exactly 0.001 kilograms. Quantities derived from measurement other than counting, however, are uncertain to varying extents due to practical limitations of the measurement process used. Significant figures in measurement. The number of measured quantities, unlike defined or directly counted quantities, are not exact. To measure the volume of liquid in a graduated cylinder, you should make a reading at the bottom of the meniscus of the lowest point on the curved surface of the liquid. Refer to the illustration in figure 1.26. The bottom of the meniscus in this case clearly lies between the 21 and 22 markings, meaning the liquid volume is certainly greater than 21 milliliters, but less than 22 milliliters. The meniscus appears to be a bit closer to the 22 milliliter mark than to the 21 milliliter mark, and so a reasonable estimate of the liquid's volume would be 21.6 milliliters. In the number 21.6, then, the digits 2 and 1 are certain, but the 6 is an estimate. Some people might estimate the meniscus position to be equally distant from each of the markings and estimate the 10th place digit as 5, while others may think it may be even closer to the 22 milliliter mark and estimate this digit to be the 7. Note that it would be pointless to attempt to estimate a digit for the hundredth place, given that the tenth place digit is uncertain. In general, numerical scales, such as the one on this graduated cylinder, will permit measurements to 1/10 of the smallest scale division. The scale, in this case, has 1 milliliter divisions, and so volumes may be measured to the nearest milliliter. This concept holds true for all measurements, even if you do not actively make an estimate. If you place a quarter on a standard electronic balance and you obtain a reading of 6.72 grams, the digits 6 and 7 are certain, and the 2 indicates that the mass of the quarter is likely between 6.71 and 6.73 grams. The quarter weighs about 6.72 grams, with a nominal uncertainty in the measurement of plus or minus 0.01 gram. If the coin is weighed on the more sensitive balance, the mass might be 6.723 grams. This means its mass lies between 6.722 and 6.724 grams, an uncertainty of 0.001 gram. Every measurement has some uncertainty, which depends on the device used, and all of the digits in a measurement, including the uncertain last digit, are called significant figures or significant digits. Note that 0 may be a measured value. For example, if you stand on a scale that shows weight to the nearest pound and it shows 120, then the 1, 2, and 0 are all significant values. A measurement result is properly reported when its significant digits accurately represent the certainty of the measurement process. But what if you were analyzing a reported value and trying to determine what is significant and what is not? Well, for starters, all non-zero digits are significant, and it is only zeros that require some thought. We will use the terms leading, trailing, and captive for the zeros, and we'll consider how to deal with them. Starting with the first non-zero digit on the left, count this digit and all remaining digits to the right. This is the number of significant figures in the measurement unless the last digit is a trailing zero lying to the left of the decimal point. Captive zeros result from measurement and are therefore always significant. Leading zeros, however, are never significant. They merely tell us where the decimal point is located. The leading zeros in this example are not significant. We could use exponential notation and express the number as 8.32407 times 10 to the negative 3. And then the number 8.32407 contains all the significant figures, and 10 to the negative 3 locates the decimal point. The decimal, or the number of significant figures, is uncertain in a number that ends with a 0 to the left of the decimal point location. The zeros in the measurement, 1,300 grams, could be significant, or they could simply indicate where the decimal point is located. The ambiguity can be resolved with the use of exponential notation. 1.3 times 10 to the 3, 1.30 times 10 to the 3, or 1.300 times 10 to the 3. In case where only the decimal formatted number is available, it is prudent to assume that all trailing zeros are not significant. When determining significant figures, be sure to pay attention to reported values and think about the measurement and significant figures in terms of what is reasonable or likely when evaluating whether the value makes sense. For example, the official January 2014 census reported the resident population of the U.S. as 317,297,725. Do you think the U.S. population was correctly determined to be the reported 9 significant figures, that is, to the exact number of people? People are constantly being born, dying, or moving into and out of the country, and assumptions are made to account for the large number of people who are not actually counted. Because of these uncertainties, it might be more reasonable to expect that we know the population to within perhaps a million or so, in which case the population should be reported as 3.17 times 10 to the 8 people. Significant figures and calculations. A second important principle of uncertainty is that results calculated from a measurement are at least as uncertain as the measurement itself. Take the uncertainty in measurements into account to avoid misrepresenting the uncertainty in calculated results. One way to do this is to report the result of a calculation with the correct number of significant figures, which is determined by the following 3 rules for rounding numbers. When adding or subtracting numbers, round the results to the same number of decimal places as the number with the least number of decimal places. When multiplying or dividing numbers, round the result to the same number of digits as the number with the least number of significant figures. If the digit is to be dropped is less than 5, round down and leave the retained digit unchanged. If it is more than 5, round up and increase the retained digit by 1. If the drop digit is 5 and it's either the last digit in the number or it's followed by only zeros, round up or down, whichever yields an even value for the retained digit. If any non-zero digit follows the dropped 5, round up. The following examples illustrate the application of this rule in rounding a few different numbers to 3 significant figures. 0.028675 rounds up to 0.0287. 18.3384 rounds down to 18.3. 6.872 rounds up to 6.88. 92.85 rounds down to 92.8. Let's work through these rules with a few examples. No. Accuracy and precision. Scientists typically make repeated measurements of a quantity to ensure the quality of their findings and to evaluate both the precision and the accuracy of their results. Measurements are said to be precise if they yield very similar results when repeated in the same manner. A measurement is considered accurate if it yields a result that is very close to the true or accepted value. Precise values agree with each other. Accurate values agree with the true value. These characterizations can be extended to other contexts, such as the results of an archery competition. Suppose a quality control chemist at a pharmaceutical company is tasked with checking the accuracy and precision of 3 different machines that are meant to dispense 10 ounces of cough syrup into storage bottles. She proceeds to use each machine to fill 5 bottles and then carefully determines the actual volume dispensed, obtaining the results tabulated in 1/5. Considering these results, she will report that dispenser 1 is precise but not accurate. Results for dispenser 2 represent improved accuracy but worse precision. Finally, she can report that dispenser 3 is working well, dispensing cough syrup both accurately and precisely. 1.6 Mathematical treatment of measurement results. Learning objectives. By the end of this section, you will be able to explain the dimensional analysis approach to mathematical calculations involving quantities, use dimensional analysis to carry out unit conversions for a given property, and computers involving 2 or more properties. It is often the case that a quantity of interest may not be easy to measure directly, but instead must be calculated from other directly measured properties and appropriate mathematical relationships. For example, consider measuring the average speed of an athlete running sprints. This is typically accomplished by measuring the time required for the athlete to run from the starting line to the finish line and the distance between these 2 lines, and then computing speed from the equation that relates these properties. An Olympic quality sprinter could run 100 meters in approximately 10 seconds, corresponding to an average speed of 100 meters over 10 seconds, which equals 10 meters per second. Note that this simple arithmetic involves dividing the numbers of each measured quantity to yield the number of the computed quantity, and likewise, dividing the units of each measured quantity to yield the unit of the computed quantity. Now consider using the same relation to predict the time required for a person running at this speed to travel a distance of 25 meters. The same relation among the 3 properties is used, but in this case, the 2 quantities provided are speed and distance. To yield the sought property time, sought property time, the equation Oh gosh, I'm sorry. To yield the sought property, time, the equation must be rearranged appropriately. Time equals distance over speed. The time can then be computed as 25 meters over 10 meters per second, which equals 2.5 seconds. Again, arithmetic on the numbers was accompanied by the same arithmetic on the units to yield the number and unit of the result, 2.5 seconds. Note that, just as for numbers, when a unit is divided by an identical unit, the result is 1, or as commonly phrased, the units cancel. These calculations are examples of a versatile mathematical approach known as dimensional analysis. Dimensional analysis is based on this premise. The units of quantities must be subjected to the same mathematical operations as their associated numbers. This method can be applied to computations ranging from simple unit conversions to more complex multi-step calculations involving several different quantities. Conversion factors and dimensional analysis. A ratio of two equivalent quantities expressed with different measurement units can be used as a unit conversion factor. For example, the lengths of 2.54 centimeters and 1 inch are equivalent, and so a unit conversion factor may be derived from the ratio 2.54 centimeters over 1 inch, or where times 2.54 centimeters, which equals 1 inch, or 2.54 centimeters per inch. Several other commonly used conversion factors are given in Table 1.6. When a quantity is multiplied by an appropriate unit conversion factor, the quantity is converted to an equivalent value with different units. For example, a basketball player's vertical jump of 34 inches can be converted to centimeters by 34 inches times 2.54 centimeters per inch equals 8.6 centimeters. Since this simple arithmetic involves quantities, the premise of dimensional analysis requires that we multiply both numbers and units. The numbers of these two quantities are multiplied to yield the number of the product quantity 86, whereas the units are multiplied to yield inches times centimeters per inch. Just as for numbers, a ratio of identical units is also numerically equal to 1, which is inch over inch equals 1, and the unit product thus simplifies to centimeters. Dimensional analysis may be used to confirm the proper application of unit conversion factors as demonstrated in the following example. Beyond simple unit conversions, the factor label method can be used to solve more complex problems involving computations. Regardless of the details, the basic approach is the same. All the factors involved in the calculation must be appropriately oriented so to ensure their labels will appropriately cancel and or combine to yield the desired unit in the result. As your study of chemistry continues, you will encounter many opportunities to apply this approach. Conversion of temperature units. We use the word temperature to refer to the hotness or coldness of a substance. One way we measure a change in temperature is to use the fact that most substances expand when their temperature increases and contract when their temperature decreases. The liquid in a common glass thermometer changes its volume as the temperature changes, and the position of the trapped liquid surface along a printed scale may be used as a measurement of temperature. Temperature scales are defined relative to selected reference temperatures. Two of the most commonly used are the freezing and boiling temperatures of water at a specified atmospheric pressure. On the Celsius scale, 0 Celsius is defined as freezing temperature of water, and 100 degrees Celsius as the boiling temperature of water. The space between the two temperatures is divided into 100 equal intervals, which we call degrees. On the Fahrenheit scale, the freezing point of water is defined as 32 Fahrenheit, and the boiling temperature is 212. The space between these 2 points on a Fahrenheit thermometer is divided into 180 equal parts. Defining Celsius and Fahrenheit temperature scales, as described in the previous paragraph, results in a slightly more complex relationship between temperature values on these two scales than for different units of measurement for other properties. Most measurement units for a given property are directly proportional to one another. Using familiar length units as one example, length in feet equals 1 foot per 12 inches times length in inches, where y equals length in feet, x equals length in inches, and the proportionality constant m is the conversion factor. The Celsius and Fahrenheit temperature scales, however, do not share a common 0 point, and so the relationship between these two scales is a linear one rather than a proportional one. Consequently, converting a temperature from one of these scales into the other requires more than simple multiplication by a conversion factor m. It also must take into account differences in the scale's 0 points. The linear equation relating Celsius and Fahrenheit temperatures is easily derived from the two temperatures used to define each scale. Representing the Celsius temperature as x and the Fahrenheit temperature as y, the slope m is computed to be m equals delta x over delta y, those are changes, equals 212 Fahrenheit minus 32 Fahrenheit divided by 100 Celsius minus 0 over Celsius, which equals 180 Fahrenheit over 100 Celsius, which equals 9 Fahrenheit per 5 Celsius. The y-intercept of the equation b is then calculated using either of the equivalent temperature pairs, or, as b equals y minus x equals 32 Fahrenheit minus 9 Fahrenheit over 5 Celsius times 0 Celsius equals 32 Fahrenheit. The equation relating temperature scales is then T in temperature Fahrenheit equals 9 Fahrenheit over 5 Celsius times temperature of Celsius plus 32 Fahrenheit. An abbreviated form of this equation that omits the measurement units is temperature Fahrenheit equals 9 over 5 times temperature Celsius plus 32. A rearrangement of this equation yields the form useful for converting from Fahrenheit to Celsius. T Celsius equals 5/9 times the quantity T Fahrenheit minus 32. As mentioned earlier in this chapter, the SI unit of the temperature is the Kelvin. Unlike the Celsius and Fahrenheit scales, the Kelvin scale is an absolute temperature scale in which 0, K, corresponds to the lowest temperature that can theoretically be achieved. Since the Kelvin temperature scale is absolute, a degree symbol is not included in the unit abbreviation K. The early 19th century discovery of the relationship between a gas's volume and temperature suggested that the volume of a gas would be 0 at negative 273.15 Celsius in 1848. British physicist William Thomson, who later adopted the title Lord Kelvin, proposed an absolute temperature scale based on this concept. The freezing temperature of water on this scale is 273.15 Kelvin, and its boiling temperature is 373.15 Kelvin. Notice the numerical difference in these two reference temperatures is 100. The same is for the Celsius scale, and so the linear relationship between these two temperature scales will exhibit a slope of 1 Kelvin per Celsius. Following the same approach, the equations for converting between Kelvin and Celsius temperature scales are derived to be temperature Kelvin equals temperature Celsius plus 273.15, temperature Celsius equals temperature Kelvin minus 273.15. The 273.15 in these equations has been determined experimentally, so it is not exact. Figure 128 shows the relationship among the three temperature scales. Although the Kelvin temperature scale is the official SI temperature scale, Celsius is commonly used in many scientific contexts and is the scale of choice for non-science contexts in almost all areas of the world. Very few countries still use Fahrenheit for weather, medicine, and cooking. All right, that's it for Chemistry, Chapter 1.